This is my 149th video on financial math for Actuarial Exam 2. You can see we're continuing to talk about Macaulay duration as we did in the last video. What is Macaulay duration? It's a measure of sort of the average time of payment of a payment stream where you are weighting it by the amount of each payment, and also the yield comes into play. This particular problem is kind of hard to describe. It's hard to understand this description here. Let me just try to break it down for you. We're going to be seeing that the Macaulay duration for an N coupon bond whose yield rate and coupon rate happen to be the same, that duration, which is a weighted average of times of payments and whose units would be in number of payment periods, like number of years, has the same numerical value but different units as, wow, this is amazing, the present value of an annuity due with N payments of 1 at that same common yield / coupon rate. Wow, that's hard to get your mind around. It's hard to believe when you start to get your mind around, but it does turn out algebraically to be true, as we will see. So this first paragraph here you see is the problem statement. The second paragraph is something extra that I added. Suppose that the yield rate and coupon rate of an N coupon bond happen to be the same. In that situation, we're going to do two things. First, show that this Macaulay duration idea, this weighted average of times of payments, is equal, numerically speaking at least, to the value of this symbol. What is that? That's the present value of an annuity due with payments of 1, N payments of 1. Valued at the yield rate, I could put a little j here, say, for the yield rate. You could also call it I. Second thing to do, evidently using the first part, using the fact that this is the same as that, the Macaulay duration is the same as that, find the Macaulay duration of a 6 coupon bond, so N would be 6, at coupon rate of 10% per coupon period, and the same yield rate 10% per coupon period. Okay, so this is a special situation. All right, we want to recall from the preceding video, video 148, what the Macaulay duration is. I introduced it differently than the textbook does, but I would like to show you that it is the same as the textbook definition in this video. From that video, the Macaulay duration was seen to be a weighted average of the times of payments, T, so T is going to be in payment periods, which could be in years, T going from 1 to N. It doesn't have to be for a bond, it's a general payment stream, though we are applying it to a bond here, where each weight is the fraction of the present value of the entire payment stream represented by the present value of the payment at time t. Okay, that's kind of a mouthful. Let's think about that more carefully now. So we could call the duration d sub mac for Macaulay. There is another kind of duration called a modified duration. But when I just say duration, we will mean Macaulay duration and sometimes denote it just by d. We could also emphasize that it depends on the yield rate, which you could call I, but I will call J to be consistent with Broverman's notation for the yield rate of bonds. And I wrote the formula for this last time as a sum. T goes from 1 to N of W sub T times T, weights of times. W sub T is the weight of time T. T going from 1 to N are the payment times, okay? These WTs are going to be numbers between 0 and 1. They will add up to 1, as we saw in the last video. And what do they equal? How do I change this description here into a formula, so to speak? Well, maybe I should also draw a timeline over here. So you've got N payments starting at time 1, then a second one at time 2, and a third one at time 3, etc. The last payment at time N. I could call those payments K1, K2, K3 up through Kn. So what is this? It's a fraction, first of all. Fraction of the present value of the entire payment stream. So I want the present value of the entire payment stream in the bottom of the fraction, the denominator. That'll be a sum. Let me use a different index of summation here initially. I'll call it M instead of T to help us more clearly see where the formula comes from. Actually, at the end, I will switch back to t, even for this summation, just to be consistent with Broverman's notation. So m goes from 1 to m, 1 to n, of what? K sub m would then be your arbitrary payment at time m. That needs to be discounted back to time 0, so I need to multiply by v to the m. I could write v to the m. I could also write 1 plus j to the negative m as your present value discount factor that you need to multiply km by. And the numerator, I want to use the particular time t. I want to discount the present value of the payment at time t back to time 0, so I want to write kt times 1 plus j to the negative t. Okay? So t, when you think about this here, is a specific time, 1 through n, specific integer, and down here, m is the variable for the summation. It's the index of summation. It's varying from 1 to n. All right, let's go ahead and use the Wt equals this to simplify this formula here, or to write it in another way that's more descriptive of what to do. Let me go ahead and write the summation again. T goes from 1 to n. I will replace Wt with this whole thing, and I can go ahead and multiply that fraction by t. I can put the t up into the numerator, so I can write this thing. Let me also use parentheses for emphasis. T times kt times 1 plus j to the negative t, all divided by the sum. M goes from 1 to n, k sub m times 1 plus j to the negative n. Now, here's the reason I used the m, to avoid confusion. This expression in the bottom of this fraction doesn't involve t. It's constant with respect to the outer summation. It can be brought out in front, and that would be true even if I used a t there, but it's more conceptually clear that it doesn't involve t if I use an m. That can be brought out into the front as a 1 over the sum that you see here. And then when you have 1 over something times something else, you can write that as a single fraction. So I can write the final formula, which you can find in Broverman's book, for the final formula for the duration here. Summation t goes from 1 to n of this thing up here, t times kt times 1 plus j to the negative t, all divided by this thing down there. And yeah, to be consistent with Broverman, I'm now going to switch back to t instead of m. Excuse me. T goes from 1 to n of kt times 1 plus j to the negative t. It wouldn't be wrong if I kept the m, but it's also not wrong to switch to a t. Just like with integrals, the index of summation and the variable of integration are just dummy variables. It doesn't matter what you call them. Okay, it's the whole summation or the whole integral that you're focused on. All right, so now that's the formula that you can find in Broverman's book. And let's go ahead and use that formula now to do the problem itself, at least the first part of the problem. We want to do some algebra to verify that this fraction here, unbelievably you might think, equals this in the end. That might seem difficult to believe. Let's take it step by step. Let's in fact focus on the denominator first. And think about the fact that we are dealing with a special situation here. We are dealing with a bond, for one thing. So the first n-1 payments are just coupon payments. And the final payment, kn, is the final coupon payment plus the redemption value, which I guess is going to be the same as the face value here. This summation in the bottom is the same as the price of the bond. It equals, by the basic formula, f times r times anj, but r is the same as j here. The coupon rate, r, is the same as the yield rate, j. Let me just go ahead and, instead of writing f times r, let's just write f times j. Times anj plus the present value of the redemption amount, which it's evidently assumed here the bond is redeemed at face value. That will be f times vj to the n. Okay? So that's what the basic formula would give us. Instead of an R, write a J here. And that's going to be handy because in this special situation, the fact that this thing has formula 1 minus Vj to the n over j is going to allow us to see that the j's will cancel. And then you can multiply this f through the parentheses I can put here if I like. And I can expand this to say it equals f times 1, which is f, minus f times Vj to the n, plus f times Vj to the n. Of course, those things then cancel, and the bottom of the fraction simplifies quite a bit to just f. Okay, that's kind of amazing. And actually, that's something you really should know intuitively about bonds, is that when R equals J, the price is the same as the face amount if it's redeemed at the face amount, if it's redeemed at par. That's something you should have already known, but now we are verifying it again algebraically. All right. Now we focus on the numerator. Evidently, for this to simplify to this in the end, the numerator must simplify to f times this in the end so that the f's will cancel. Okay. To help us think about what the numerator equals, it might be good to draw another timeline and imagine a different kind of annuity that this numerator is going to be representing the present value of. Think about it here. We are still thinking about the bond. Kt, when t goes from 1 to n minus 1 at least, equals f times j. But we're weighting them. We're multiplying them by t. T is 1 at first. Let me draw a number line with an annuity on it, undiscounted amounts. The first undiscounted amount would then be 1 times f times j. And the second undiscounted amount would be 2 times f times j. And the third one would be 3 times f times j. Now, again, the numerator does involve discounting those things. The last one would involve n times f times j, but also n times f. Let's write it this way. Let's put n times f up here, and then plus n times f times j down there. That represents the last one, because Kn is f plus f times j. But I wrote it this way to highlight that this part of this imaginary annuity that I'm just imagining to help me simplify this formula is f times j times your basic increasing annuity. So, thinking about the formula for the present value of this, that would be f times j times ia nj. And maybe now you see where this is heading. If you happen to remember the formula for ia, the present value of an increasing annuity, a basic increasing annuity, you know that it involves a double dot, the present value of a basic annuity due. Okay? If you didn't remember that, that's something to look up. I will write it down here in a second, but that's what you would get for this part that I circled in red here. Then you also have the present value of n times f. That'll be n times f times Vj to the n. Okay? So again, there's a formula for this that involves a double dot. Hopefully you have it memorized. If you don't, look it up. It's a double dot nj minus n Vj to the n divided by j. Once again, the j's cancel, and with what's left in this thing, you could put parentheses in here if you like. Conceptually, you want to multiply the f through. So you're going to get f a double dot nj minus n times f times v to j to the n, which is going to cancel with that plus n times f times vj to the n. And there we have it. This all simplifies to f a double dot. okay? And therefore, combining these two facts, the fact that the green, the denominator there equals f, and the purple numerator here equals this, the f's cancel, and we can say, therefore, 3 dots, dmac equals this, the f's cancel, and we're left with a double dot. An amazing fact, I think, okay? Completely unexpected in my mind that this would be true. Think about the units, though, carefully. dmac, if the coupon period is years, say, this is in years. It just, numerically speaking, it equals this, which would be in dollars, for example, if the money is in dollars. But numerically, they are equal in value. All right, so that's the first part. Now we can do the second part pretty quickly. Find the Macaulay duration for 6 coupon bonds. So N would be 6 at coupon rate 10%, which is the same as the yield rate, 10%. J would be 0.1. This was part A of the problem. For part B of the problem, the duration for that particular bond will be A double dot 6.1, which is the same as 1.1 times A without a double dot, 6.1. And so now we need to just use the calculator. 1.1 reciprocal, there's V to the 6th power. Subtract from 1, divide by 0.1. A6 equals 4.35526. Multiply that by 1.1. And you get a final answer of about 4.7908. That is the duration. You've got 6 payments total here if you want to conceptualize this here. If you imagine the face amount being 1, for example, well, let's imagine it to be 100. 1, 2, 3, 4, 5, 6. If you imagine the face amount of this bond to be 100 and the coupon rate is the same as the yield rate is 10%, you have payments of 10 from time 1 to time 5 up until your last payment of 110. And we're saying based on the interest rate of yield rate of 10%, the average time of payment, so to speak, this weighted average, this Macaulay duration is about 4.79, which would be about there. Okay? The fact that this amount is so much larger is what weights it more towards 6, though these amounts, like when t is 1 or 2, get weighted a little bit more compared to these amounts because they are discounted less. Okay? And that is the end of this problem. Thanks for watching.